Hey guys, so today we're going to continue with the topic of vectors. And in a previous lesson, recall that we talked about adding vectors together, so like a vector v plus a vector w. And we talked about multiplying a vector by a scalar, as in multiplying by a normal number, right? So k would be the scalar here, times vector v, and that either stretched or shrunk the vector, right? But you might wonder, well, can you multiply a vector with a vector? So is there such a thing as vector v times vector w? So again, the overall topic for today is vectors, and the answer is yes, you can multiply a vector with a vector. In fact, there's multiple ways to multiply vectors together, and today we're going to just talk about one, and it's called the dot product. And this naming should make sense because remember, a product is the result of multiplying, right? So a dot product is a type of multiplication we do with vectors. Now, the name dot product also makes sense because a dot is how we indicate this. So for example, we might write vector v dot vector w, and there we would be finding the dot product of those two vectors. But before I show you how the dot product works mathematically, there's one important thing we should talk about. So for example, let's consider multiplying two numbers together, right? So like two scalars. Well, you take one number, which is a scalar, right? 3, for example, times another scalar, 3 times 2, and the result is yet another scalar, right? But think about when we multiplied a scalar with a vector. So for example, k times v, where k is the scalar, v is the vector. Well, what was the result of that? K times v, well, the result was another vector, right? A stretched or shrunk version of the original vector v. So one important thing to understand about dot products is that the result of a vector dot another vector, the result is actually a scalar, not a vector. So for example, maybe we multiply v and w, and we get negative 10. So again, the result of a dot product is not a vector. It is a scalar, a normal number. Now, it turns out mathematically, a dot product is super simple to find. But let's talk about the formal definition, just so we can get used to mathematical language, okay? So first of all, we have let vector v equal v sub 1 comma v sub 2, and vector w equal w sub 1 comma w sub 2. And all this is saying is, let's just take two arbitrary vectors, where v sub 1, whatever number that is, that's the horizontal component of v, and v sub 2, whatever number that is, that's the vertical component of v. And same for w, right? W sub 1 comma w sub 2, that's the horizontal and vertical components of w. So again, we're just taking two arbitrary vectors, whatever they are, v and w. So now the dot product. It says the dot product or inner product v dot w is given by, so v dot w equals v1 times w1 plus v2 times w2. So what is this saying? Well, what are all these letters? It's saying the product equals, as in you find it by v sub 1. What is that? That's the horizontal component of v, right? Multiplying that by w sub 1, what is that? That's the horizontal component of w, right? So multiplying the two horizontal components together, plus, what is v sub 2? That's the vertical component of v, and w sub 2, that's the vertical component of w, right? So basically, you take the horizontal components of each of the vectors, multiply them, plus take also the vertical components of the vectors, multiply them as well, and then whatever you get, you add them. And if you think about it, indeed, the result of that is some number, right? Because all the horizontal and vertical components are numbers, you multiply them and add them together, the final result is some number. It's a scalar. So here's our first example with actual numbers. And again, it's super simple, super straightforward. It says find the dot product of u equals 3 comma 7 and v equals 1 comma negative 5. So the dot product u dot v. Note that the letters of the vectors doesn't really matter. So again, how you find the dot product, take the horizontal component of one of the vectors, so 3, times the horizontal component of the other vector, so 1, and then plus, add that with whatever you get when you do the same, when you multiply the vertical components, right? So 7 for one of the vectors, and then times -5 is the vertical component of the other vector, right? So times -5. As always, be careful with negative numbers. So 3 times 1 is positive 3, plus 7 times -5 is -35. Add those together, your final result is -32. So that is the dot product of vector u and vector v. So that's actually it for the basics of dot products. So now the question is, why do dot products matter? Why do we care? Well, dot products, there is an actual physical application of it. It has to do with physics and forces acting on objects and stuff. But I can't assume that all of my students have the necessary background in physics to be able to really work with that. So instead, today we're going to talk about a more abstract application of the dot product. And that abstract application is the angle between two vectors. So here we've got two vectors here. One of them's pointing above and to the right. The other one's pointing below and to the right. And when we're talking about the angle between two vectors, we have to be careful because in general, we draw vectors all over the place, right? When we're sketching a situation, maybe there's multiple objects or multiple forces in the situation. So we draw one vector over here, the other vector over there. But when we're talking about the angle between two vectors, we specifically mean the angle between them when we put the vectors with their tails together. So like this, right? Now the tail of each vector is at the same point, and the angle we're talking about, the angle between the two vectors, is this angle right here, right? And in general, we'll label that theta. So again, that is the angle that we're talking about when the vectors are positioned this way with their tails together. So don't forget, even if vectors are drawn separately like this, for example, when we're talking about their component form, really that component form means the vector with its tail at the origin of a coordinate plane, and then the components tell you where the head is. Tail at the origin of a coordinate plane. So anyway, how do we find the angle then? So here's an example. Find the angle between these two vectors u and v. Also sketch the situation to make sure that your answer makes sense. So let's do a rough sketch of the situation first. Let's see, u is 2, 6, so right 2, up 6, so maybe something like this. Here's u. And then v is -5, -1, so left 5, down 1, so maybe something like this. And again, the angle between the two vectors is this angle right here, right? Theta. And notice that this angle is obtuse, as in it's a big angle. It's bigger than 90 degrees. So our final answer then should be more than 90 degrees, right? But again, how do we actually find the angle? Well, with this big formula here, and it looks kind of complicated, so let's break it down. So first of all, notice that this formula has a theta here, and of course that represents the angle we're trying to find. So that's what we're trying to get by itself, that's what we're trying to solve for. Then there's a cosine in there. Now on the right side, we've got this giant fraction, and notice on the top it says vector u dot vector v. So this part says find the dot product of the two vectors. So that's dot product. Now that you know how to find, what about the bottom? So we've got vector u in these like vertical bars, this absolute value looking thing. and vector v in these vertical bars as well. And in a previous lesson, we said that represents the length or the magnitude of that vector. So this right here, that represents the magnitude of u, and this right here represents the magnitude of v. So this is saying, okay, here find the magnitude of u, or length of u. Same for v over here. And so now we've got the cosine of the angle that we want equals the dot product on the top of a fraction. Remember, that's a number, that's a scalar, divided by the length of one of the vectors times the length of the other vector. Now notice that each piece of this formula we already know how to find. So after we find what this big expression here evaluates to, then we have that cosine theta is equal to whatever that number is, and to get theta by itself, we can just inverse cosine on both sides. So let's take this example step by step. First, let's find the dot product here. So dot product. We know how to do that now, right? The horizontal component of one of the vectors, 2, times the horizontal component of the other one, so -5, plus the vertical component of one of the vectors, 6, times the vertical component of the other vector, -1. And let's see, this is 2 times -5 is -10, plus 6 times -1 is -6, so -16. So far we have that the top of this fraction, this big fraction, is -16 here. Now let's find the length of u, that's this right here. Length of u. And if you recall from a previous lesson, well, u is like starting from the origin right 2 up 6, right? So that's like a right triangle with one length 2, one length 6, and the magnitude of the vector we want to find is this right here. Let's just call it x. It's a right triangle, so of course all we're going to do is use the Pythagorean theorem to find it. So 2 squared plus 6 squared equals x squared. Left side, 2 squared plus 6 squared is 40 equals x squared. And then to get x by itself, square root both sides. We'll just keep it exact. So x equals square root of 40. So that's the length of the first vector. That's what will go here, square root 40. And then similarly, let's find the length of v. So this one now. Well, the vector goes left 5, down 1, so it's a right triangle like this. Left 5, down 1, and again we're trying to find the magnitude. We have -1 squared plus -5 squared equals x squared. And if you do the same type of algebra we did earlier, you will get the square root of 26 is the length of v. Let's put that here. So now we've found all the pieces we need except for the final one that we're trying to find, right? Theta, the angle. And so we can just do some algebra to figure theta out. So look, we have cosine of theta equals -16 on top, and then root 40 times root 26 on bottom. And all this is something you can just stick into your calculator, right? It's just some number. Although be careful how you type it into your calculator. So you got -16 divided by, and then we have to multiply the bottom first. So in your calculator, you're going to want to put that in parentheses. So square root 40 and you times square root 26. Or maybe in your calculator, you don't calculate this all in one step. Maybe you calculate it step by step. Whatever you do, your final answer should be around negative 0.4961. So now we've almost got theta by itself. All we got to do is take the inverse cosine of both sides, right? Inverse cosine. These go away because they cancel. So we get theta is around cosine inverse of negative 0.4961, which is around 119.74 degrees. And that's our final answer. And if you remember our diagram from earlier, so one of the vectors points this way, one of the vectors points that way, and yeah, that looks around 119 degrees, right? So our answer is correct, and that's how you find the angle between two vectors. Now, one last quick thing. Let's say we're not being asked to find the angle between two vectors exactly, and instead we just want a general idea of how large the angle is. So here it says, determine whether the angle between U and V is acute, obtuse, or right, as in, is the angle less than 90 degrees, greater than 90 degrees, or exactly 90 degrees. And in this case, we actually don't have to deal with this huge formula. We don't need the whole formula. Instead, just finding the normal dot product, so just this part, will actually tell you whether the angle is acute, obtuse, or right, even though it won't necessarily tell you exactly how many degrees the angle is. So here's a little table that summarizes that. So you find the dot product, and if the dot product is positive, right, if it's a positive number, then the angle between the vectors is acute, less than 90 degrees. If the dot product is a negative number, then the angle is obtuse, right? It's big, it's greater than 90. And then if the dot product is exactly 0, then the angle is a right angle. It's exactly 90 degrees. And here's a vocab term. If the angle between two vectors is exactly 90 degrees, so if they're perpendicular like this, right, then we say that the two vectors are orthogonal. So that's a new vocab term that basically means perpendicular, orthogonal. Now, just to illustrate all this, recall that in our previous example, we saw two vectors that looked like this. So one of them was like this, one of them was like this, and we did find the angle exactly, but if we only wanted to know whether the angle is acute, obtuse, or right, at some point in our work, we found that the dot product was negative 16. So negative dot product, obtuse angle, right? So it makes sense. Clearly that angle is greater than 90 degrees. So that's it for this lesson. As always, if you have any questions or feedback, feel free to contact me.